The next of our derived forces we will talk about is the normal force. Now, the word normal means, in mathematical and scientific terms, it means perpendicular to a surface. This symbol, of course, means perpendicular. A normal force, then, is any force perpendicular to the surface of action. And if you notice in our little concept map here, we're on our second of these forces. So cutting right to the chase to help understand what the normal force is, we ask, how do we measure the normal force? The normal force is actually what we get when we step on a scale. That is actually what is being measured. You step onto a scale, like so, and what happens is you could think of it as there being these little springs inside, and when you step on it, these springs are compressed, and then the springs, as you step on them, they get compressed more and more and more. It gets harder and harder to compress them, and then there's this balance point reached. So you're actually measuring the force that the spring is pushing upward. It also happens to be a measure of the force acting downward, because all of this is sandwiched due to the action-reaction pair, which is the Earth and the person. And you've got these intervening forces here. But the short of it is, how do we measure its stepping on a scale? And so we have 126.4 pounds. Oh, that's the force. Haha, the force. Now this force plate works just like a scale, except it gives it works just like another scale, except it's going to give you a readout like 735 newtons. It will give it to you in newtons. And we will actually be using this exact same force plate in the coming days in the laboratory. Another way to measure a normal force is another force sensor, which we'll be using in the coming days. And this one basically, like the two above it, has effectively a little spring inside, like so. And when you interact with it like this, by pushing on it, the spring gets compressed. Or if you pull on it like this, the spring gets stretched. So it can measure both compression forces, where you're squishing, and tensional forces. So that's how we can measure force. But what is normal force really? I've already alluded to this. And I find this sort of thing exciting when you look at it to see what really causes things. And basically, a normal force is that whenever materials are in contact, it's the force in all instances where there's contact between bodies. So what we have here is sort of a scanning, tunneling electron microscope where we can get down there and see the atoms or the molecules. And what we have when we see these surfaces interacting is, it turns out it's actually they're not touching everywhere. There's all these gaps due to the holes because of the unevenness of the surfaces. But then when we get really, really closer and we look at the material on top, this green, this lime green, and we have this darker blue like so, what's really going on there is we have electrons. These are the electrons that we're seeing, the electron clouds in these atoms. And we know electrons have negative charges, and like charges repel. So what we're actually seeing is repulsion force between these two electron clouds in the materials. And what is not obvious then is that these electrons never touch each other. As you get closer and closer, the force gets larger and larger and larger until it approaches infinity. And so these electrons are not touching each other. They're actually floating. This surface right here is not touching. This surface is not touching, and they're not touching at all. They are actually levitating upon each other. So this leads to a really interesting fundamental type problem, which is, since these two surfaces are not actually in contact with each other, is it possible for anything to touch anything else? Since all things are made of matter, all things are made of atoms, the outer layer of which is the outermost portions are electrons, and you cannot make electrons get so close that they touch each other unless you're inside a star where the pressures are that great, nothing can ever touch anything else. And you may say, well, wait a second, I could take my finger and I can push on my cheek and I can feel the pain. Well, all you're feeling is the intense compression of the tissues. As you're pressing your skin, the skin is moving ahead of your finger. And that pressure is the true pressure you're feeling that's compressing your nerves, that causes you to have that feeling as the fluid moves around inside your tissues. But make no mistake about it, you're actually not touching yourself, or anything else for that matter. You're just feeling the effects at a very small distance of the other matter interacting with the electrons. Now, that's a really fun metaphysical thing to think about. So let's apply this concept to a book sitting on a table in the simplest level. So we've used this before. We've got a table. We have a book like this, and the book is 2.6 kilograms, and the table is 12.8 kilograms. Well, ultimately, what's going on? Well, the first thing we know is that when we look at this thing, the acceleration is 0. We would agree the book sitting on the table, the acceleration is 0. Well, if the acceleration is 0, and we know the net force is the sum of the forces, we know F net is ma, and F net is the sum of the forces. If we look at the actual forces that are occurring right here, what we have is the force acting on this block. There is a gravitational force of attraction downward between the Earth and the book. And there is a normal force acting upward. And so our force is our force of gravity plus the force normal. Now, if we know the acceleration is 0, and that is equal to the force of gravity plus the force normal, well then the force of gravity plus the force normal must add up to 0. Subtracting force normal from both sides, we see the force of gravity must be equal and opposite to the force normal. Notice that we just did the beauty here in applying Newton's second law. We could intuitively look at this and say this is static equilibrium. The forces must be balanced. We can set out to do Newton's second law. F net is the sum of the forces. F net is ma. We list our forces. A is 0. We observationally determine that. So 0 must be Fg plus Fn. Therefore, the force of gravity must be equal and opposite to the force normal, which indeed it is. So now we can determine how large each of those forces is. Well, first of all, we can determine the force of gravity acting on the book. That is Fg equals mg. And the mass of the book is 2.6, and gravity is 10. So we have 26 newtons. That is the force of gravity. So that's minus 26 newtons. Well, if we know this thing is minus 26, well then the force normal must be positive 26. And it works together beautifully and consistently. Now, it's easy when we're doing a case like this to apply Newton's second law. But we always set it up this way to keep track of the forces that may be more complicated later. So now I want us to examine quickly the normal force. Is it fundamental or is it derived? Well, you could say since it's not one of the four, it's not fundamental, it must be derived. And then we ask ourselves, is it contact or at a distance? This is a common distinction that physics teachers ask students. Is the force a contact force or is it at a distance? And ironically, this is a force that's ostensibly about contact, but what we've seen when we look at this close up, there can't possibly be any contact with anything. So what we mean by contact in this case is that it's like observationally in contact, not theoretically in contact. So we would consider the normal force a contact force. But understanding forces in this way, this distinction about contact or at a distance, is not really helpful. But I wanted to introduce you to that terminology because if you access other resources than those that I will give you, or you may even see this terminology when you get to college, professors might use it. I'm not sure why they would. But in any case, you may come across it in other venues.